Today's lesson, section 9.2b, the dot product, part 2. Here we're going to talk about projections and work. So a projection is kind of like our component of vector u along vector v. So a projection of vector u onto vector v is going to be the vector that's parallel to vector v and whose magnitude is the component of vector u along vector v. And it's denoted as such, where it's the shortened word of projection, so PROJ, and then kind of like if you were writing a log function, you'd write the vector u as a bigger vector, and then vector v as like a sub-vector kind of thing. Okay, so looking at my pictures here, I'm kind of trying to describe what a projection is. Now remember, take note, projection of vector u onto vector v is a vector. It's not a scalar like the component one was. This is an actual vector, so you're going to have an A portion and a B portion with this one. So for vector u, it doesn't matter how long vector v is, but it's just going to be that, still that kind of that shadow casting down. So it's going to be the vector that's kind of parallel, so it has the same direction as vector v, but it has the magnitude of the component that we got from vector u. Okay, so that's how they're. So it's like taking, kind of like with one of our problems that we did in the last one with unit vectors. You know how if you wanted a unit vector, and let's say you wanted a certain length, you would find the unit vector, so dividing it by the magnitude to get it to a certain value where the direction ended up being 1, and then you multiplied it by the length because 1 times your length gives you your new length. So this is kind of the same thing, actually. So let's look at the calculation formula for it. So the projection of vector u onto vector v is going to be your component of vector u along vector v. So we've already seen this portion of the formula, so that's nothing new. So the dot product of your two vectors divided by the magnitude of the vector that you're going in the direction of, and then now you're going to multiply it by the unit vector of your vector v. So you take vector v divided by the magnitude of it. Okay, so that's how we kind of calculate projections. Now before that, we can kind of do something with our vector u. Okay, sometimes they're going to ask you to resolve a certain vector. So to resolve a vector u, all that means is to break it into two different vectors. So you're going to say vector u sub 1 and vector u sub 2. Okay, and they both represent two different things. Vector u sub 1 is going to be the vector that's parallel to vector v, and we already kind of said that there's a vector that's parallel to v, okay? And then the other vector is perpendicular to v. So what that means is for our vector u sub 1, that's actually the projection, and that's the definition, is that the projection of u onto v is going to be parallel, and so when we resolve something, we're breaking it up. That's kind of what we're finding is the parallel one. And then the other one that's perpendicular, now it's easy to find once you have the projection, that's the hard part. You just take your original vector, so vector u, and you subtract the one that was parallel, so vector u sub 1, that gives you u sub 2, okay? Because remember, what you're doing is let's go back to our pictures, okay? So let's say we take this one, so this one is like your vector u sub 1. This vector right here is like your vector u sub 2. So when you add those two, you get vector u. So that's why it's written as this, because if I subtract the u sub 1 over to the other side, I've solved for vector u sub 2. And so then that's an easy way of finding the other one. Okay? So here's an example. Let vector u be negative 1, 2, and vector v be 4, 5. They want you to resolve vector u into the two vectors. So the one that's parallel to V and the one that's perpendicular to V. So first things first, we need to find a vector u sub 1. Oop, I wrote the wrong number. U sub 1, which is the projection. Okay, so like our formula said up at top, let's make this a little wider for us. Okay, we want to take the dot product of the two vectors and then divide that by the magnitude of vector v. So the dot product would be -1 times 4 plus 2 times 5. And then the magnitude of v would be 4 squared plus 5 squared. Okay? Now the other one, you just have the vector v, so vector v is 4 comma 5, and doing the same thing. You are finding the magnitude, so 4 squared plus 5 squared. Okay? So now I need to simplify. So -1 times 4 is -4, plus 2 times 5 is 10. And then at the bottom, 4 squared is 16, plus 25. Nothing to do with the numerator here, but same thing, 16 plus 25. Okay? Then you have -4 plus 10 gives you 6. And then 16 plus 25 will give you 41. And then you still have your 4 comma 5. And then square root of 41. Okay, now notice what happens here. Okay? So here, this is a scalar, the 6, and then we can distribute into our vector. Notice that these two things are the same, so square root of 41 times square root of 41 should just get you 41. So, if I have 41 in the denominator and I distribute the 6, or the scalar value, into my vector, 6 times 4 gets me 24, and 6 times 5 gets me 30. Now I can rewrite my vector for u sub 1 as 24 over 41, comma 30 over 41. Okay? So then that's one of your answers. There's your u sub 1 vector. Now you need to find the other vector, but like I said, the other vector is a little easier to find. Let's go with a different color here. So I want to subtract the first vector minus my original vector minus u sub 1. So then now, -1, comma 2, minus 24 over 41, and 30 over 41. Okay, so remember I got to change those. So -1 would be -41 over 41, and 2 would be 82 over 41. Okay? So then now, -41 minus 24 gives me a -65 over 41. And then 82 minus 30 gives me 52 over 41. Okay, so then there is my u sub 2 vector that I was looking for. So then I can find both. Okay? In class, I'll have a warm-up for you so that we can kind of practice this together if you'd like. Okay? Now let's move on to the next thing. So something called work. Okay? Now work, W, done by a force F, in moving along a vector D, is denoted by work equals force times D. Okay? But only when force is in the direction of motion. Okay? So force is moving in the same direction as D. If not, okay, if force is not moving in the same direction, then only the component of force affects the object. So the force is kind of like just pushing down on it. Like, let's say your direction of movement is moving it east, but force is pushing it like down, then force is the only thing working on it. And it's not really doing anything to it. So it's like it's not moving the object, it's just a waste of energy. Okay? So here you have a component of force, or vector F, along vector D. And so that was the other way we could have written it. Remember, is the magnitude of the force vector times cosine theta. Okay? That's the component part that we talked about in the last video. So now, if I'm doing work, which is force times D, the force part is actually the component value. So the magnitude of force times cosine of theta. Now times the magnitude of your direction. Okay? That's what gives us this force times, or the force vector times the direction vector. And so recalling our formula that we've had before, that's kind of what they're doing. So the U is like your F and the V is like your D. So then I could multiply both sides by the magnitudes of both, and that's what gets me this formula. So that's why it works. So the dot product is also another way of doing it. But if you don't have the dot products, or you have an angle for them and given like weights, then it's probably easier to use the force, the magnitudes of the force times the cosine of theta. Okay, so two different ways of finding it. So don't restrict yourself to one or the other. So example 11. It says a force F is 3, 6 and moves in an object from 2, -4 to 10, 1. Find the work done. Okay, so here, because you don't have any angles, you can't really use cosine theta, nor is force and direction put in like weights or anything like that. So, like foot-pounds kind of thing. So that means we need to use the dot product here, but I need to first find the vector 4D, because they don't really give it to me outright. So now I need to take 10 minus 2, 1 minus a -4. That gives me 8, and then plus plus, that gives me 5. Okay, so there's my direction vector. So now, for work, I can take the force vector, the dot product of the force vector and the direction vector. So then now I get, it'd be 3 times 8, and then plus 6 times 5. So it gives me 24 plus 30, which gives me 54. And here we don't really have any labels either, so one way we can describe it as units of work. Okay? Because usually we have like foot-pounds or something like that. Okay? So example 12 says a pallet is pulled horizontally with a force of 25 pounds at an angle of 45 degrees to the ground. Find the work done to move it 50 feet. Okay, so a quick picture of this would be, let's say this is your pallet. Okay, and so let's say there's something here for somebody to pull. Okay, so this is 45 degrees. Okay, and then if he's moving 50 feet, and then this is your force is 25 pounds. Okay, then they want you to be able to find the work done. So that means we need to use the other formula. So the work could be found as your direction vector and your force vector, or the magnitude of the force vector, times cosine of theta. So you have your direction vector. Okay, so it's 50, 0. And then you don't really have the force vector, but you have the magnitude of the force vector, which is 25 pounds. Okay? The magnitude of the direction vector is pretty easy as well, because 50 squared plus 0 squared is just going to be 50 squared, which they cancel out to give you 50. Okay? So, you have those two values. Now, so 50 times 25, and cosine, you have your angle is 45, means that you can plug in or multiply. So let's plug it in. So 50 times 25 gives you 1,250, and then cosine of 45 is going to be the square root of 2 over 2. So let's multiply those out. Times square root of 2 divided by 2 is going to be 883.88, and here's where your real usual label is foot-pounds. Sometimes they use newtons as well for force, and we'll have some problems wherever we use those. Okay, but for this example, it would be foot-pounds because we kind of just combine the two together. Okay, have fun.